This is a more subtle point. So I motivated local operators this way. However, not all local operators correspond to deformation with the same geometric data. And I will correct myself. So I think that nobody left, basically. Pasha?
Hi, Andrei. So actually, I was confused. So in your discussion, is the difference between your and Lio's definition that in Lio's definition in CFT you would allow all conformal weights, and in your definition you want only conformal weight 0?
So I think that
which is a weird thing to ask of an observable.
I think that in Lover's definition, um, any vector field associated to the boundary is a local operator, because his construction procedure is undone.
No, but that's fine. Well, undone, and so what? It's still something that's. So what?
No, it's not every vector field, because some vector fields cannot be holomorphically do not have holomorphic continuation into the disk. So not any.
Oh, that would select probably like positive conformal weights or something.
I see. So I don't want to. So I don't want to say that. I don't want to make a conclusion right now. So let us say that we have two definitions.
No, okay? I think we actually agreed on the definition, and I kind of accepted what you said, that basically we will have the sequence of decreasing balls. We will have maps from view of smaller balls to view of bigger balls, and we will have projective limit with respect to the weak topology induced by correlators.
But the question is, what are these maps, right? Because there are two kinds of maps. So I think there was one map given by considering the partition function for the annulus. That's one map. And the other is claiming that there is some other sort of canonical identification that's different from that one.
No. Coming from the annulus, I think, and there is no.
Coming from the annulus is what Andreas calls undoing.
But there is no any other identification, I think.
Well, there's a claim that there's another identification.
So I mean, if we say that in Andrei's definition we do not need this identification, because we just say that all correlators should converge. Okay.
So in my definition, we study class of equivalence of convergent.
I mean, so we do not care if they're identified or about any topology on this. I think, and I identify them by this by this thing, but we do not actually care.
So yeah, in that sense, I was happy with your definition.
And I think it's exactly the holomorphic vector field. I mean holomorphic in the punctured.
Punctured. Then it doesn't. It's not important, because everything is holomorphic if you don't care about extending if it blows up at the puncture.
No, because it could be. I mean, there are fields on the circle which cannot be promoted to the holomorphic fields in the punctured disk. if their negative part is too divergent, it will happen.
Oh, that's okay.
But then we should say that it can be promoted to the field in the puncture disk, and then I think it is the same, like germ of the vector field in a punctured disk.
So now I see that there, that there is the following. So but there is a distinction. So in what I propose, the local observable is a class of equivalence, and that has to be computed, and the correlator of this class of infinity of equivalence is defined. So another definition is the following: take a ball, glue something there, and then the question is, of course, in which metric, because a priori there are different analyses. There are different analyses. So no, definitions are different.
No, I don't understand. So in conformal field theory, so if you, I think with lowest definition, you would get like all let's say fields of all conformal weights, and you just transport them to another radius by multiplying them with just appropriate powers of the change of radius, and that's fine.
It's a boundary. So,
yes.
okay.
Yes, you change the radius of the boundary. You rescale appropriately the operators with the power of the change of radius. Do you mean that
it's another thing?
But do you mean that you want to select a part of that space which corresponds only to operators of dimension 0?
No,
no, definitely not. Definitely not. There are some issues if we add things of different weights, about issues about convergence. Do we require it to be convergent in some sense or not? And if not, then why? And if yes, then in what?
So once again, so there are two definitions, and one definition states that so what is first question is, what is the space of local operators? So in my case, the space of local operators is is a space of is a vector space of good sequences over nil sequences, and
but okay, don't you get a good sequence out of any state on a circle of any radius by extending it by this parallel transport?
No, because suppose you have so for me the basic object is a map 0 R1
yes
V star DB PR.
Yes,
that I call V. So if so these maps naively depend on R1. So for any R1, I can have such maps. However, it is clear that since there are equivalences of them, I mean these equivalences, that if maps differ, so if I have one map, let me call it V1. Let me have another map called V2. this equivalence class does not depend. Suppose that R2 is bigger than R1. This equivalence class does not depend, LO,
Mhm.
does not depend on the behavior of V2 in the region between R1 and R2. It's just like a limit of the sequence does not depend on its first finite number of terms.
Yes.
It's just like we defined, so this is similar to the definition of the tangent vector. So tangent vector is a class of equivalence of curves. However, we are interested only in the behavior of curves near the beginning. Here, situation is the same. Consider two families. If these two families differ in the region, that is separated from zero, they lead to same local operators. It's equivalence class. So this definition is actually very close to definition of tangent vector. So it is actually an equivalence class such that there is a lot of things that are equivalent.
Sorry, I say no. That still didn't help me. So why is it not the same? Why are those things that we are computing still not the same as the space of states for a circle?
Okay.
I mean, I think I can answer this
try
question.
to make
Mhm.
comparison.
So
Okay.
let me, Andrei, I think I can answer this question.
Mhm.
If you are, Andrei,
Mhm.
can I
Yes.
suggest something? So yes, okay, we can identify these spaces for
Mhm.
different circles, and they will give which will give these identifications, or I would say we will have some maps between them, and which will correspond to transfer by annulus. And they will give just the same values on any correlator. So
Yes.
this is now we consider the projective limit. But it's not just a projective limit, it is a projective limit with a topology, weak topology induced by correlators. So we can have such an element that does not come from any constant sequence, but it is approximated more and more closely by circles of lowered radius. So we could actually have such in the example we could have a field with such Taylor expansion that it actually does not converge in any radius, even very small radius. Only thing we require is that it can be put in any correlator.
Yes.
So a priori it could be bigger, but I'm not sure how it works.
But no, actually, that sounds rather strange. So here I would really like an example, I guess.
So I think it is actually like one space should be the closure of another.
But yeah, no, I'm not sure that such a thing can happen in a reasonable, let's say, conformal field theory. But no, I don't know. But that sounds.
I mean, what actually you can put in P. You will have if it's a field of some weight, like z to the power k d by dz, then it clearly belongs to the both of these spaces.
So
And
what you decorate a point with in CFT is actually what you decorate a little circle around P with. So in that sense, yeah, you are actually just taking decorations of a circle, and you're just saying that there's a rule how you identify different circles.
But I mean, there is also, I mean, if you add things of different weight, then maybe we could have weaker convergence. That's all I'm saying. I mean, in Andrei's definition, we could have a weaker convergence.
So I am a bit puzzled because at least in my definition, you do not need to so at least in my definition, I understand what correlator is. And in Ljova's definition, so if we consider analysis like Ljova proposed, right? I mean this identification, it means that we are not doing anything. In particular, once again, here we put V2, here we put V1. If V1 is given from V2 using this.
No. V1 maps to V2.
Using
Annulus operator of V1 gives V2.
Using which annulus?
Between V1 and, I mean.
With which metric?
This one.
With a given metric.
This one.
So,
this
so
annulus.
So
exactly
means,
this one.
So it means that the correlator of local observables, that the space of local observables should in your definition, should be exactly the space V.
No, because this operator might be actually non-invertible. Or it could,
but you see, maps
are what?
Maps, of course, are invertible, at least in all known examples. It's one thing, and another thing is that we should know what the correlator is.
So, but I know what the correlator is. You can put either V2 or V1.
Yes, but your correlator.
And it will give the same answer due to the factorization property.
Yes, but it means that what you call, so in your definition, you should do the following. You should take a circle with the radius R2, take V2 belonging to this boundary. Okay?
Okay.
Then you compute such object, you call it correlator. Okay.
Sure.
Then you say, define sequence that I am proposing by doing the following thing. Take a ball of radius R1 and plug this annulus here.
Sure.
But then by undoing this procedure, okay.
So I want to find such V1 that it gives V2 by the application of the operator coming from the annulus. Okay.
So if V1 that you have at radius R1 is such that it corresponds to V2 at radius R2, Yes?
Yeah.
That means that by shrinking the thing, you are not, you have a constant.
Yes.
So you have constant map. And these sequences are sequences of, so you propose constant sequences. Of course, constant sequences have limits. But I am not sure that that it is what we would like to call by local operator. And
Also, I'm not sure why you call them constant. They are isomorphisms. But I mean, okay.
I mean, they're constant in the sense they give constant values for all correlators.
Yes, in that sense, they're constant.
Yes, but what Andrei says is that we can have interesting non-constant sequences. And what I'm saying that whatever they are, they should live in some closure of our space in like the weakest possible topology. Like we put the topology that all correlators converge and then just consider the closure. And then it is what we need. That's I'm saying.
So, I mean, calling them constant sequences is a little bit at odds with the, you know, the standard thing that you would write that these observables are acted on by the kind of conformal Hamiltonian e to the L0 plus L0 bar, right? So things are being rescaled. You're just sort of you're ignoring this rescaling if you are applying this isomorphism.
so it's so actually these definitions are different, and because observable that Lyoba proposed is of course it is a good sequence. Yes.
Can we have a good non-constant sequence that doesn't reduce to the constant one? Can I see it in the one example? You can write even if I wouldn't be able to read half of it, it would be better than not seeing an example. Like I will be most likely not able to understand it, but I prefer to see it. Like one particular example of it being interesting, non-constant, good sequence.
Okay, you see, I can give example of such sequences. I can give example of such sequences explicit. If I know some operators, then I can construct other operators.
So just write it down like
okay.
anything.
Okay. Well, let me give an example.
If it will be in language that I cannot understand, then bad for me, but better than nothing.
So suppose I have a disk. So when I have, so I'll explain the stuff in this language. That should be so-called operator product. Suppose we have O1 and O2. And you know this object.
Okay.
So it's a disk. So this thing depends on here is 0, here is say R over 2, and here is R. Okay?
Sure.
Imagine that I know this. So imagine that I have local operators. I want to define new local operators. Then what I do? I tend R to 0. sometimes I have O2 of R over 2, O1 of 0, and I know that it goes universally, say like 1 over R2, with some operator O3, plus regular terms.
And this O3 is called operator product.
And that's why, and that's why I want to say that I can do things like this. I put here O3, and I also know what this is, and I put here 1 over R2, and then I take the limit, R going to 0. And this is a new local operator described by this procedure. In the sense that I gave, because it's a sequence that definitely converges in the weak sense. And we know such objects in current algebras, for example. So this is an element, this is an element, the difference is also an element, and they definitely have limit.
But Andrei, they're also equivalent to a horizontal sequence, like or constant sequence. They can also be described in the previous language.
So definitely these two things are not the same, because okay, this stands still, however this thing moves. If you consider horizontal sequence, it would be just consider them for the finite distance and
yes, I agree that as it is given, the sequence is not constant, and it is not obvious that it can be made into a constant sequence, given like what just has been said.
These are these sequences that I keep in mind.
But it is equivalent to a constant sequence.
А почему?
Вычисление.
It's not the difference is finite. The difference between this sequence and constant sequence is finite. It's something finite. That goes away.
So okay, in the end, it will be some element of
So
it will be a vector field with values and
operator in the weak sense. Okay, let us call this weak local operators, elements of the vector space.
I mean, so okay.
And it is interesting to see if there is a constant sequence.
No, but so you apply, this is kind of a nice kind of Siegel way of presenting things, but if you apply it to some kind of explicit CFT, then you will obtain some explicit, I don't know, finite observable, which you can then represent by constant sequence again, right? Some, I don't know, some normally ordered product of some local observables that you already know.
So suppose we know what local observable is, then constant sequence, as far as I understand, so is the following.
So there will be a sequence of things that you can attach to circles that is constant.
Yeah,
in the previous sense.
If we already have a local operator, then this thing is a constant sequence.
Right. So you can promote anything to a constant sequence kind of somehow tautologically.
So I would say the following: suppose you know local operators at the very beginning, then you can find a constant sequence.
Mm-hmm.
However, I don't understand so I understand what is the constant sequence, and I understand in which sense constant sequence could be plugged in. Another thing, now I see the difference. The difference is between non-constant sequences and constant sequences is that non-constant sequence depends on some auxiliary data. I mean the metric that you use in constructing things, and weak operators do not depend on geometrical data outside the point. They just do not depend on it. So if you make a diffeomorphism, you will make you see you will change the metric, or if you change the metric, you would violate the notion of the constant sequence. So constant sequences are probably not what you have in invariant way. So constant sequences are not things that depend on the local geometry in the vicinity of the point. Because
I do not understand.
You need to start constant sequence from somewhere. If it's constant,
you're saying that the annual separator depends on the metric,
yes,
which you use to identify. Yes,
yes,
sure,
yes.
Sure. So your notion of being constant, somehow this constant thing is kind of his abuse of language. But yeah, applying the annual separator, yeah.
But I mean, if I
So once again, the main issue is, suppose you have a solution, so we need to formalize it. Suppose we have a solution to a single set of axioms. Somebody gave it to us. I don't know how. In some examples, it's possible to write it down explicitly. In free fields, for example. It's very explicit something. However, we need to introduce a new notion. Yes, we need to introduce a new notion, and this notion should be invariant. Now I see the criteria. So since it's a system, diffeomorphism should act on the system.
Yes, that was my initial point of starting point.
And if it's a local, then the correlator of so-called local operator should not depend on vector fields that vanish as a marked point with infinity order.
So I think that the difference is like instead of considering the germ, we consider the Taylor expansion.
No, it's the difference is that that yes, yes. Now I see the difference. That's why I prefer what I have better, because it's
But okay, can we agree that these two things are like your space is just closure of
no. The space that you consider depends on more data, and it is not invariant under
how
the.
it is dependent on more data? I do not understand still.
So
I think it depends on the point P and geometric data in the and germ of geometric data.
okay, so let us discuss this construction again. Okay, so what do you propose? So what we need to have? We need to have, from my point of view, the following structure. Given a point P,
That's too high. We cannot see anything.
Given a point P and geometrical data defined in the as small vicinity as it is possible around P, we need to find a number or a map. Okay, let us put here only one boundary X. So what should we do in your procedure? As far as I understood, your procedure is to say that let us just cut out
Any pointed ball.
any pointed ball, put some vector V here, and say that yes, this is and that this correlator is a correlator of a local observable at point P.
Yes, sure.
And at least it is clear that that this definition does not fill the geometry inside this ball. It contains no information.
But I mean, we also consider the class of equivalence. If there are two balls, one is inside another.
Okay.
We will identify them.
So let us consider two balls. Okay, so let this be a big ball of radius r.
By the way, I do not care about radius. You can just draw any topological ball.
Of course, I'm just drawing it to simplify things. So this is big.
I'm just pointing out that this is invariant. It doesn't depend on any coordinate chart or anything like this.
Of course, but I want to draw some picture.
Yeah, sure.
So here is 0. Here we have a circle of the radius r1. Here we have a circle of the radius r2.
Yeah, sure.
Okay. Here we have the metric, let me call it G1. Here we have the metric that we call G2.
Excuse me, I thought we have a fixed geometric data on our manifold, right?
Okay, so we have a yes, of course we have fixed geometric manifold. So G2 is such that
is a restriction of this data, and G1 is a restriction of this data. Am I correct?
Yes. So here we have metric that is okay.
So it's not metric. In our case, it's a complex structure, I think, but okay, geometric data.
So here we have G2, and let me call here G21. Okay.
Sure.
So G2 is here, and here is nothing, and here is G21. Okay, so here that's why I just omitted. So I'm writing the borders. One thing, another thing. So this thing is S2, and this thing is S1. So here we have the following data. Here we have I that depends on geometrically G2, G21 on the center. That belongs to V dependent star of S1. S1 has radius R1 times V star, and here is SR. So it's one thing.
Somewhere there is no star. On one of the spaces there is no star. Yeah, like this.
Here we have E that depends only on G2. That belongs on V star. Here we have S2. Then we have FSR. We can say it's okay. Let it be very big. So SR is something far away. So here the topology and geometry here is not that important. To show it. To show it, I can even put here, I don't know, a handle. To depict it, I put it handle, and this handle is the same here and here.
Sure.
Just to show that it's not necessarily a disk. Okay?
Mm-hmm.
But so this is the data that we have. And we also have another thing. We have an annulus with the metric G21. And here we have, so this is, here is S2, and here is S1, and here we have I, S1, here we have I, depending on G21. That belongs to V star at S1 times V of S2. Okay. So here we have three pieces of data. Okay.
Sure.
So the question is, how to define something new, that is, and here is SR, I put here a handle, here is a point P, and something like O. So how to define a function of what? And here is a metric G, by the way. So EI should depend on G, on what else? on O. Okay, P is the same. That should belong to V of SR. Okay? Or actually, how to no, let me put it honestly. You said, sorry, and here there should be some V star to some U star. So this U is a space of operators.
Space of local observables.
Yes. So having these three data, so okay, they give dependent families. How to define this?
Why don't we just say that U is V of S1 or V of S2?
We need to define this this map. We have this.
So I don't really understand the question. I mean, we have we define U as V of SR for any R or arbitrary small r by and we identify them.
So okay, so we define U. Okay, so
okay, is this U dependent on G? What is the dependence of U on G?
So U, very good question. So U should define on the germ of G at point.
So then I think my definition works.
Okay, so please say it again.
So okay, we have a sequence of maps between V of SRs for different Rs.
Of small r's, okay. So.
Okay, small r's, we have a sequence of identifications. This sequence of identifications depends on G.
So look, here is this sequence of identification.
Yes, one term of this sequence is written here, and it depends on G.
It depends on G.
Yeah, sure. So now we use this identification and define the map U as the space, any of the spaces, like we identify them. This is U.
So no, here is this space. So let me ask you, what is the space U? U is a space.
V of S epsilon for any arbitrary epsilon.
Okay, so our r's are small enough. So you propose, okay? So you
yes.
propose that U is V of say S1.
S something, and I will identify them for different radii, and this identification will be dependent on G.
So U is V of S. Let me see. U. So you say that U is V, depending on. So associated to what? So
S epsilon, and epsilon is arbitrary small.
No. Okay. So everything, all smalls are small. Okay.
Okay.
So
sure.
all smalls are small. So so you want to say that U is what? So U is so at least let us take one choice, and then let us see that other choices are the same.
Yes, yes, sure.
You say that U is
V of SR for
V
small
of
r.
Okay. Then so U is V of SR, and and since left hand side is independent on R and right hand side depends on R, we need to choose some kind of identification.
Yes.
So what is this identification?
Maps dependent on G, maps coming from the annuli between different.
Okay, so let me try to see. So V depends on, so there are two definitions. Definition one, that U is V of S of R1, okay?
Mm-hmm.
Definition two, that U is V on S on R2.
Sure.
Then it's now we come to tricky thing. These spaces are isomorphic as a vector spaces.
Yes.
Ищу в Яндексе.
And but then you also say that there is a map that identify that, and there is a map that V of S R1 is okay applied to I S1 S2 annulus, yes. So of course these spaces are identified. However, this identification depends on you see what is striking. This identification depends on the metric G21.
Yes. Yes. It should. Definitely should.
However, each particular space is not. So space here is that does not depend on the G21 metric.
Yes, yes, sure, because I can take smaller r as the definition. So, I mean, I think it's clear that if you will change the metric away from any small radius, then I think it's clear that the spaces U are canonically identified. So they actually depend only on the germ of the metric.
So you see, the question is how to say how the question is how to say what is U, because identification between these two spaces depends on metric, and S and spaces V SR1 and V SR2 do not depend on metric.
They, I think, so what's the problem?
The problem is how to make this definition, because
So,
U is this space and U is also this space.
Okay, but U depends on G, okay?
No, I mean U should depend on the germ of G.
But it depends on germ of G because because we can remove any number of balls from the sequence and U will still be defined.
So now I see the problem. So now.
But there is no problem here.
No, you see, I want.
Yeah, no, there is clearly no problem in this point.
I still I want to understand do you see what's written here?
Yes, sure. But I don't like what's written here. What you actually should write is the sequence of V of SRs for different Rs, and then say that U is some limit of the sequence, say projective limit.
Okay.
But because these maps are all isomorphism, we do not actually care.
Okay, so let me write it again, okay? Because I want to understand what happens. So okay, so let us consider sequence. So 2 is bigger than 1. Unfortunately, let's 2 make smaller than 1 because okay. So let us consider the sequence. R1 bigger than R2, bigger than R3, etc. Okay?
Sure, sure.
Okay? Then we have V. So let me just say that SR1 is, let me call it S1. Okay?
Sure, sure.
To simplify, so there is V S1, V S2, etc. V,
And there is a sequence of maps.
and there is also, of course, and there are also maps. Let me call them I12, depending on G12.
I would prefer I to 1, but okay.
Okay.
So if they are invertible, there is no significant difference.
Let us imagine that they are invertible, but for me it's not different. It's not that different. So how would you like to put these maps? In which direction?
From right to left, I think is better.
From smaller to bigger.
Yes, yes, much better. But if they are isomorphisms, there is no difference.
Still, so still there are maps.
To 1, 3, 2.
N minus 1 n. Okay.
In n minus 1.
In n minus 1. Okay. In n minus 1. That maps V of Sn. So smaller to bigger or bigger to smaller?
Smaller to bigger.
Smaller to bigger.
But smaller ball is a bigger number. So.
Yes, but we okay. Smaller what? Smaller ball or
smaller ball to the bigger ball, increasing maps.
Smaller ball to the bigger ball.
Yes. Okay. So I will compose them with the main body of the correlator.
Okay, and here these diffeomorphisms depend on metric IG.
Sure.
Okay.
And so U is the projective limit of this diagram, or just any limit because they are all isomorphisms, so we do not care.
So maybe here is my. So you want to say that U is what?
Projective limit.
N going to infinity. Yes.
Of this diagram.
Of this diagram. Great.
And I can remove any number of starting spaces from this diagram. So why don't I? So it clearly depends just on germ of G. That's
yes.
that is, I think it's pretty clear.
So my problem. So it's so the problem is not that there is not such a diagram. The problem is in my ignorance. So my ignorance is that I don't understand what does it mean to take such a limit.
It just means that you consider a sequence of elements which sequences of elements which map to each other.
Let me write it. So you consider a sequence. So maybe in this case, you would agree with Siegel. Okay. So you consider the sequence R1 is bigger. Okay. So you consider the sequence of elements V1, V2, etc.
Yes.
Related by these isomorphisms.
I mean, if it's isomorphisms, then there is nothing to actually do. But general definition is you consider the sequence and Vk goes to Vk minus 1. Okay?
Sorry,
Vk goes to Vk minus 1 by the map given in the diagram.
Okay, okay.
That's the definition.
Okay.
That's called projective limit. You can also endow it with some finer topology, and it might be reasonable to do in some cases.
Okay, so now it sounds interesting because because okay, so you have these sequences.
Yes. And I state that I can remove any number of elements from this diagram, and it will not change the limit. Any finite number of first elements, and it will not change the limit. I think it's pretty clear.
So what does it? Okay, then okay. So now I see. It's because you were in the mathematical department, and I was in the physical department. Okay. So maybe these things are equivalent. So in some sense, you want to say that local operators are just S infinity.
Just the limit of this sequence, yes.
But
I also think that.
But what do you mean? So suppose okay. So suppose you have such sequence. Okay.
Sure.
So there is something that I don't quite understand. Suppose there is such sequence of things with this isomorphism. Okay.
Sure.
Let me think for a moment. Okay, and suppose there is another sequence.
Sure.
We can check if there are equal or not, of course.
Yes, then.
Okay. So this is a sequence made by all of these elements, and
so let me give you another definition that you will maybe like a bit more. So suppose these spaces are Hilbert spaces, and the maps are how do I say it? Operators of finite norm of norm at most constant, or at most some constant. Okay, norm at most one. Let's say norm at most one. Then the following definition will give what you are saying. Let's not.
Sorry. What do you mean operator of norm one? Because identity has norm infinity.
No, it has norm one. I mean, norm is.
What do you mean by norm?
Norm is supremum of AV of norm of AV divided by norm of V.
Okay.
Then identity has the norm one, and any projection has the norm one.
Okay.
Banach norm. So I mean, I'm just saying that okay, if you say that all these things are isomorphisms, then actually nothing happens. That's I can ensure. But so if they're actually not, then something interesting might happen.
Okay, let me now I have a question. So I understand what is this sequence. This I understand. But what is the definition of a limit?
So the space of such sequences is called U.
The space of such sequences is called what?
U. It is a limit. Space of such sequences is a limit.
No, so the space of such sequences, what do you mean it's a limit?
It is called the limit of this diagram. And I will denote it by U. It is dependent on G, and I can prove that it actually depends only on germ of G around the point P.
Okay, so space of such, okay, Mama. So space of such sequences, you call U. So so this space. So, but in this case, I would say that given any element of V, say of S1, I can generate such a sequence.
Yes, if they are isomorphism, yes, then nothing interesting happens.
Now let me continue to ask questions.
Sure.
So here we have space of such sequences. In which sense the space of such sequences is independent on G?
It is dependent on the germ of G, but it is not dependent on the behavior of G away from any arbitrary small ball.
That's what I'd like to understand.
Yes, sure. You can remove any number of terms from this diagram and canonically identify U.
But it means that, you see, you know that the okay, so here is the space of such sequences. Okay, I try to understand. Here is the space of such sequences. How to and this space of sequences as a vector space is determined by any S1, by any Sn.
Yes, sure. Because they're all identified. It's actually the same space. Under this identification, it is the same space, if you think about it. Now let me ask. So since they are all identified, how to compute? So I should ask several questions. First question is how to compute correlator, and first question of U. Sure. Identify it with any Si, V of Si, and then compute the correlator. And the answer will be not dependent on which Si we will represent it with.
Let me see. So this. So that's what you are saying. In this definition, okay. In this definition, local observables are the same as V's.
Indeed.
So we cannot choose
Пока, Паша.
Пока-пока. Нужно бежать, извиняюсь. Ага.
Но мне тоже скоро.
Да, ну спасибо, интересный вопрос. Угу.
Может, даже дойдем до куда-то. Удачи. Good luck.
Лёва?
Да, sure.
Значит, возник такой один вопрос. Значит,
So I think we still have non-Russian speaking participants.
Okay, so,
possible.
Okay, so let us keep English. So how to enumerate them? So I have
So there is some caveat.
Okay, so still there is something that I don't understand. Space of such sequences, since isomorphisms depend on G, I cannot say that space of such sequences is independent on G.
But you can say, okay, let's consider sequences, but they actually start from some number k and go up. Like, do not go lower. We can prolong them, but we do not at this point.
And also when we compute, so I like your definition now better than my definition.
But I mean, so there is a k-width. These definitions might be non-equivalent still.
And because of G dependence.
No, not because of dependence. Not they might be equivalent, not equivalent because of the topological reasons. Like if you actually have these maps of topological spaces, then you need to induce some topology on the space of sequences. And it might be non-trivial. So like the question of whether any local observable can be approximated by local observables of this kind is still like Pasha said that in the actual example, they are indeed approximated. I mean, they are indeed identified with a constant sequence, like in the operator product. It is indeed true, but I mean there is some technicality which could arise if these maps are. I mean, if I'm correct, these maps are not unitary.
Which?
I of G something.
No, there are by definition.
But in the Euclidean case.
Euclidean case, yes.
They are not unitary. Then.
Yes, they are not unitary, but they are isomorphism.
But I mean, they could have some non-trivial norm, and then you could want to induce this norm on the sequences. You could say, oh, okay, I want them to be L2 something, or I'm not sure.
So what time is it? So we need to keep
7. I mean 7 p.m. Moscow.
7 p.m.
5 minutes short.
Okay, so let us stop this discussion, and so after all, seminar is of course for discussion, but we made a mistake. We should start discussion, and then we should postpone it to the out of seminar time. Okay. So I mean that we should continue to discuss it among us. We need to find the way how to organize discussion.
I have like half an hour till I need to go, so we could call up.
I have to go right now.
Okay, sure.
Okay. So So where is Zoom? Okay. So if there is somebody left, we should close the discussion. So, okay. So I don't know how to, okay.
So I think you could just stop the conference, or I don't know.
Okay.
Bye-bye.
But it's, how can I stop?
I mean, you're an organizer, so you can stop it. Definitely.
Yes.
You can press like, okay,
No,
that's
so
not.
I stopped the video translation. Where should I?
You press quit, and then you choose stop
Okay.
for everyone.
Okay.
Я предлагаю созвониться когда-нибудь и поговорить.
Да.
Я тебе письмо напишу.
Okay, so, okay. So I'm closing conference.